Today here I am going to say about the ASIC flow design. That is the backbone of every custom chip you'll find in your smartphone, data center or car. By the end of this PPT, you will understand each stage, why it matters and the key pitfalls that cost team time and money. So first we'll start with what is ASIC. ASIC stands for Application Specific Integrated Circuit. It is a chip, so basically it is not reprogrammable. Just like FPGAs are reconfigurable, we can implement program it again. We cannot program ASIC again. ASIC is a chip designed to do exactly one thing and to do it better than any general purpose processor can. Think of a neural engine in Apple's M series chip or a Google's TPU for machine learning. Notice the comparison here. A CPU is flexible, it can run on any code, but that flexibility costs power and area. FPGA sits in the middle. You can reconfigurable the logic after manufacturing, which is great for prototyping, but it's bigger and less power efficient than a fixed design. In an ASIC gives you the best power, performance and area. But once you tape it out, the logic is frozen. So you would better get it right. So it is difficult to implement. Like there are a lot of steps for the ASIC flow design. We'll go ahead with that now. ASIC design flow overview. First of all, we get to the specifications. Like, what do we need? Like, suppose I am going to make adder. So, what adder should I? What are the specifications required for an adder? Full adder, like half adders we require. So that is the specification. Then we go for the RTL design, in which we write the Verilog code for the full adders that will comprise of the half adders. Then we'll verify it, like we'll verify using our test benches. We'll simulate, and there are many formal methods for verification. We'll use UVM or we can use system verilog as well. Then after verification we do the synthesis part, in which our our RTL description, like the Verilog code is converted into gate level netlist, and we can do it with the Genus software, and there are many other software as well. Then one we get the gate level netlist, and after that gate level netlist we do the physical design, in which we first do the floor planning, in which we define the die, core, and the power layout. Then we have the placement, in which we place the standard cells like our gates, and gates or gates, like where they are going to be placed. And then we have routing, in which we connect all nets using metal layers. Then we do the tape out. And then we go for the tape out after the verification, like our DRC and LBS check is done. Then we go for the tape out, in which we do the GDS2, in which we made a GDS2 file, that is the last file for our tape out. So we'll do the process in details now. RTL design and verification. We write the Verilog code for the verification, for the RTL design. You're, uh, and then we have the verification, like as I told earlier, you can do it using UVM, that is universal verification methodology, or we can use the system Verilog for verifying our documents code, sorry. Then we have logic synthesis, in which we write the RTL code. A synthesis tool converts into gate level netlist. RTL codes is the behavioral description of the design. Technology library is the standard cell from the foundry, and constraints like the timing, area, and the power utilization. Then we have the physical design, that is the backend of our, then in which we do first the floor planning, in which we define the chip area, macro placements, and IO pads. Then we have the placements in which we place the standard cell, including gates like AND, or NOT, and all the standard gates we have. Then we'd go for the clock tree synthesis, in which we optimize clock in such a way that we have less delays for our program, and for our modules to be specific. Then we have the routing, that is we connect the wires cells with the metal wires. And then we have DRC and LBS check, in which we have the design rule check, that is our design matches the design like our layout matches with the design of the RTL code which we have written. And we have the LVS check, in which like what I have written matches with the foundry, which rules of the foundry I am using. Suppose I am using a 65 nanometer or 180 nanometer, so the rules of that foundry should match with my design. It should not be like that I am doing something else and the foundry rules are different. Then we have the tape out fabrication and text test. After the GDS2 file is done, we go to the mask making, that is the photolithographic mask created. Like then the wafer fab, it will take months and weeks, dicing and packages and ATA test, and then we have go for the production. Key metrics and design trade off. Everything in ASIC comes back to the PPA triangle: performance, power, and area. There are These three are always in tension. If you increase the pipeline depth to get a higher clock frequency, you improve performance but add area and increase latency. If you widen your data paths for throughput, area and power both go up. If you move to a coarser process node, you might cut cost per wafer, but your area balance. This trade space is why chip architects earn their salaries. Every architectural decisions needs to be tracked back to the concrete PPA impact. RTL is written is expensive. Reversing them after synthesis is very expensive. Reversing them after tape out is catastrophic. So we should write a RTL in all the flow of our ASICs. RTL design is the most basic and most important part. Like if it is wrong, you have to go back to the, like if it goes wrong, then you have to go back, and which can cost you a lot. So we should design it perfectly, and several tests should be made before fixing it or before taping it out. So let's we have the summary: specification, agreeing on what you are building and why are you writing the code. RTL design, hardware thinking in Verilog or VHDL. Verification is 60 to 70% of your effort, the most important investment you make. Synthesis, RTL to gates, meeting timing with the Foundries library. Physical design, floor plan through DRC or LVS check. Tape out and fabrication, GDS25 out, silicon back. So, this was all about the ASIC design flow. I hope you understood, everyone, and thank you.